power of symbolic execution to the fight against malicious Excel4 macros. This work is the result of the collaboration between 4 people, myself, Nicola Ruaro, Fabio Pagani, and Stefano Ortolani. Fabio Pagani and Nicola Ruaro are working at UCSB in the SEC lab, while myself and Stefano Ortolani are working at the threat analysis unit at VMware. Excel4 macros are used in malware mostly to as the first step in a malware infection. An Excel file with Excel4 macros is sent, usually as an attachment, and then the macro gets executed and download another component that makes the malware more persistent. There are many families that use this mechanism to achieve a first foothold on the computer of users. We observe this with TrickBot, DanaBot, GoZ, Zloader, you name it. We have been tracking at VMware this threat since the very beginning of 2020, and we have observed a continuous evolution of the techniques that are used to avoid detection and avoid analysis. So what are Excel4 macros? It's a legacy feature of Excel that has been made obsolete by VBA macros. The difference between Excel4 macro and VBA macro is the fact that VBA macro are enabled by default, but they cannot access the underlying operating system, while Excel4 macros need to be enabled explicitly, but then they have full access to the underlying capability of the operating system. And for example, they can execute commands using PowerShell, and they can start programs, and so forth and so on. So if you look at your common idea of Excel4 macro, they're limited to the workbook they're operating on, and you cannot interact with the environment. Excel4 functions instead can access the Win API directly, they can access the file system directly, and therefore they're a very powerful mechanism to gain access to the computer in which the Excel4 spreadsheet is running. It's important to understand how they work. There is, in this spreadsheet, there is a first cell called the auto open cell where the execution starts. After that, execution continues in the underlying cell until there is a transfer of execution that can happen in a number of ways. For example, using the goto function, the run function, or a user-defined function. At the same time, the data in the cell can be modified dynamically using the formula and formula fill functions. So, for example, a formula function could write some code in terms expressed in terms of function in a specific cell, and then the program could jump to that cell, and therefore there is the chance of doing dynamic execution of code. To give you an idea of what the bad guys do with these capabilities, this is an example of a macro that checks if there is mouse and audio in the underlying system. This is done so that they can avoid being analyzed in sandboxes that don't have a mouse or an audio system attached. We saw evasion of this type of technique. For example, while the previous example was a hidden macro sheet, in the new example we saw the very hidden macro sheet that requires a manual operation in order to expose the content of the actual macro. And in addition, we see new evasion tricks. For example, a check on the size of the display. Other things that we saw throughout 2020 and 2021 is the use, for example, of the char function in order to collate together letter by letter the whole content of a macro, or the use of time dependency. For example, in this case, there is a macro that uses a specific day as a key to actually decrypt the contents of the macro. So, for example, if you do it in the wrong day, you obtain just gibberish. But on the right day, you have the correct macro. Well, this, of course, can create all sorts of problems. And another technique that is used by malware authors is the use of register in order to create custom names for specific function. So the register function in XL4 macro can associate any kind of label to any kind of function. And by doing this, the malware authors try to avoid signature matches and static analysis on the code itself. So you can see from this that there are problems with obfuscation because there are so many techniques that can be used in order to obfuscate a malware. Some techniques can prevent detection. Some can even help detection. However, the deobfuscation problem is still very hard. And we need deobfuscation because we want to understand all the possible behaviors of a specific macro, not the ones associated with a single execution. And also, we want to extract the indicators of compromise. And I don't know if you noticed in the previous slide, you can see that there are a number of domains that are used or executable that are used, and that information is important in order to create threat feeds that allow systems to detect this type of macros reliably. So at the moment, deobfuscating these macros is an error-prone manual task that requires a lot of manual work, mostly because static analysis does not work because it's heavily obfuscated. And also dynamic analysis only gives you one sort of thread of execution. So we want to automate the obfuscation, but how can we handle all these environmental checks that make a particular macro only work if the right boundary conditions are correct? How can we guess the right value? And here we introduce the power of symbolic execution. This is a program analysis technique that uses symbolic values in order to represent all possible executions, at least in theory. So the basic idea is that in symbolic execution, you interpret the code, and whenever there is an input from the outside environment, you keep that value symbolic. So when a conditional statement is found and the conditional statement relies on one of these symbolic values, instead of taking a single decision, you fork a new state, so you sort of proceed both ways, and depending on in what branch you decide to progress, you add a constraint over the value of the symbolic variable. At a certain point, you might reach a point of interest in your code, and at that point you can ask a constraint solver to automatically provide you with a value that satisfies the constraints that will take you to that point. And you can use this technique to obtain automatically deobfuscated code. Well, let me tell you a little bit about symbolic execution with this example. So we have very simple code, and you can see at the very beginning we have a state, and we read some input. So our variable x at this point is a symbolic variable. So we don't know what value it is. It's not 5, it's not 7, it's just a symbolic value. So we sort of like wait to make a decision on that particular value. Of course, in the following line, we actually compute a value based on that symbolic value, and so we have to keep track of the fact that y is x plus 1, so a symbolic value plus 1. And then we encounter our first constraint. We have a conditional y greater or equal to 10, and so we have to sort of split our execution in two possible states. One that will be followed if the constraint y less than 10 is true, and one if the constraint y greater or equal 10 is true. And you go on. Then, for example, you can have another if then else. in this case is based on X, symbolic variable, and therefore the relevant state is split again to track all possible outcomes. But at this point, we are at the interesting code. And so we can now concretize this state, and we can ask the solver, hey, give me a value of X that actually will drive the execution of this code to this point, to the interesting code. So you can avoid testing for the errors, you just get to your code, you have your state, and you get the magic value that will lead you to the place where you want. And you already can understand how this can lead to the point where you will have the interesting de-obfuscated code. And at this point you say, wait a minute, how do you do this? Well, Nicola Ruaro will explain the nitty-gritty details of how this is done.
Hello everyone, and thank you Giovanni for the introduction. So now we'll talk about our approach and implementation of the Symbexcel symbolic execution engine for XL4 macros. To start off, and before delving into the details of symbolic execution, I would like to talk a little bit about concrete analysis. Concrete analysis is a good tool for post-infection analysis and de-obfuscation of XL4 macros. It will not execute the XL4 sample, but it will instead load the XLS file into memory and start interpreting all of the instructions from the entry point down to the actual execution of the malware payload. Since the initial environment configuration is not known, it is possible with concrete analysis to use brute force and forced execution in order to automatically figure out what the correct environment configuration is and sidestep the environment configuration. A good example of a concrete analysis tool for XL4 macros is the XLM macro deobfuscator developed by Dissect Malware, which is a great tool that poses the basis for our symbolic analysis approach. Now, the problem with concrete analysis is that first it will need some human input, because either a human analyst will need to manually inspect the malware sample and figure out what the correct environment variables are, or it will need to manually inspect the sample and figure out what variables we should reinforce and how to efficiently reinforce them. This, as you can expect, will quickly get ineffective because as the malware starts to use more environment variables and the search space becomes larger and larger, this approach will no longer work. Symbolic execution, on the other hand, will understand how these environment variables are generated, propagated, and used during the execution, and will allow us to reason more formally about the environment and leverage this additional information in order to solve the constraints in the most efficient way possible. Our architecture is composed of three main components: the loader, simulation manager, and the solver backend. The loader component is where the XLS file is loaded into memory. The simulation manager is essentially a state orchestrator and will, as you can see from the image, during the execution manage multiple states where every state has its own copy of the environment, memory, and constraints. Finally, the last component in our architecture is the solver backend, which is where we keep track of the constraints and we will solve constraint to proceed with the symbolic execution. We will now talk briefly about these three components, and we will start off with the loader. The loader is where the XLS file, which comes in the bfate format, will be parsed and loaded into memory. The loader will create an initial simulation manager and initialize its memory and its environment accordingly to the file that is just loaded into memory. So at this point we have two choices in order to implement the loader. We can decide to implement the loader in a static fashion or in a more dynamic fashion. An example of a loader implemented in a static way is the XLR D2 library developed again by Dissect Malware, which is a good approach, fast but less robust than the dynamic alternative. So if you want to use a more dynamic approach, what you can do is instead to use the Windows Component Object model, which allows us to interface directly with Excel, so load the file into memory and in this way avoid many of the evasion techniques that we commonly see in the most modern wave of XL4 malware samples. The second component in our architecture is the simulation manager. The simulation manager is essentially a state orchestrator, as we have already said. So what it will do is initialize an initial state that will start the execution from the entry point. It will then implement a step function that transitions from one state to the successful state while taking care of updating the memory, the environment, and the constraints. Every state will contain its own copy of the memory, environment, and constraints, where the memory contains the cell values, formulas, cell information, and the defined names. The cell information are like the font that is used, font size that is used in the cell, etc., while the defined names are global names which are shared all across the spreadsheet. Environment variables are what is used by the malware authors for sandbox detection. An example of some environment variables is the window height and the operating system which is in use. Since the initial environment configuration and the correct environment configuration for the malware execution is unknown, what we do is associate a symbolic variable with each one of these environment variables, and this allows us to figure out later during the execution what the correct value for that particular environment variable is. Finally, constraints are what will characterize the malware execution, meaning that the malware will take one branch or another branch when executing a conditional instruction depending on the constraints that are set on the state. An example of a constraint is window height greater than 390, and this type of constraints are propagated throughout the execution to the successful states. So every time that the step function is called, these constraints will be propagated to the successful state. So the step function is what will take care to execute every cell and every formula. The first thing that the step function does is to parse these formulas in order to generate an abstract syntax tree, or AST. This is done by using an extended Bacchus normal form grammar, or EBNF, and a look-ahead left-to-right parser, which we implemented using the Lark library. After parsing the formula and generating the AST, the step function will dispatch the execution to the correct formula handlers, which will take care of updating the memory, accessing the environment, generating and adding new constraints, or creating new branches whenever a conditional instruction is executed. Now, in order to make this all more clear, let's look at some examples. So in this case, we will start execution from the cell A1, and the cell A1 contains the formula char with the parameter 72. The char formula is very common in this kind of samples and essentially translates from the ASCII representation of a character to the character itself. And so in this case, it will update the memory and write the character H to the destination cell A1. After executing the cell A1, the step function will continue and step into the cell A2. The cell A2 contains the formula getWorkspace14. GetWorkspace is a special type of formula that will access the environment and in this case read the value of the environment variable workspace14, which corresponds to the workspace height. After reading the value from the environment, this will write its value into the cell at the address A2. So you can see how the symbolic variable is now no longer only in the environment, but has also been propagated into the memory and will be used later for further computation. After stepping the cell A2, the cell A3 will be executed, and you can see here that a conditional instruction is executed. The if formula takes three parameters. First, the condition itself, then the true branch, and then the false branch. In this case, you can see that the condition is symbolic, and so we don't know if we have to execute the true branch or the false branch. And thus we generate two branches, write the correct values to the correct cells, so 75 and 76 to the cell A3 in the two branches, and finally generate and add the correct constraints to the two states. We will add the constraint workspace 14 greater than 390 to the true branch, and workspace 14 less or equal than 390 to the false branch, and then continue with the symbolic execution. Now, at cell A4, we have a slightly more complicated formula. As usual, the step function will parse this formula and generate the corresponding abstract syntax tree, which you can see in the image. As you can see, one of the leaf nodes in this case is symbolic, and it's the variable workspace 14 again. During the execution of the formula, the handlers will propagate this value and generate a symbolic expression that will be then written into the cell A4. Now that we've seen some of the examples, let's have a look at our solver backend. What we use for our solver backend is the Z3 SMT solver, which is a very common SMT solver, and we believe that the most interesting use case for our tool is the execution of a symbolic payload. However, what I mean with a symbolic payload. So let's look at an example. Let's go back to our example, and when executing a cell A5, you can see here that we execute the formula fill, which takes two parameters, an expression and a destination cell. In this case, the expression is a concatenation of multiple characters. So the first thing that the handler for the formula will do is to read these characters from the memory, concatenate them, and write the result finally into the destination cell A6. As you can see, the values that we read from the environment are not all concrete. Some of them are symbolic. So we will have a new symbolic expression, which we marked as symbolic expression 2, that is going to be written to the cell A6. However, after executing a cell at A5, the step function will continue execution and execute the cell A6. A6, however, contains a symbolic expression, and we don't know yet how to execute a symbolic expression. Obviously, the solution for this is to concretize the values and generate multiple possible concrete solutions that we will later execute in our symbolic execution engine. However, how many solutions do we have here? In this case, the expression is pretty simple. It will read 4 variables from the memory, 4 cells, and 2 of them are concrete, cell A1 and A3, and those only have one solution, while 2 of them, A2 and A4, are symbolic, and both depend on the symbolic variable workspace 14. Workspace 14 is an integer symbolic variable, so it will have 2 to the power of 32 solutions, and you can imagine how this is not what we want to do. We don't want to execute 2 to the 32 instructions or generate 2 to the 32 branches. But the question now becomes, can we do better than this? And our answer is that yes, we can. And the optimization that we introduce are 2. The first one is the concept of observers. We strategically introduce some observer variables into the Z3 expressions in order to make the constraint solving more manageable. An observer variable is essentially an intermediate variable that will hide a sub-expression and observe its value throughout the execution. Looking at the cell A4, the expression that is now contained in that cell is workspace 14 greater than 390 plus 84, which is then a Boolean sub-expression workspace 14 greater than 390 plus a concrete integer 84. However, when we are symbolically executing the sample and we want to query all the possible models associated with this cell, What we will get in this case is all the models associated with the symbolic variable workspace 14. But what we really need are only the two models associated with the true or false solutions of the Boolean subexpression. What we can do is introduce an observer variable which is going to be equal to workspace 14 greater than 390. Thus, the value in the cell A4 will now be observer plus 84. And now that we perfectly understand that this expression can have at most two solutions, and we will be able to query the models and continue with the symbolic execution without an additional overhead. The second optimization that we introduced is called smart concretization. So the problem here is that even when introducing the concept of observers, we will still have many solutions associated with every symbolic variable. What we can do, however, when solving and concretizing an expression is to filter the possible concrete values considering the XL4 grammars. We already know which values are correct or incorrect, and we can then use the XL4 grammar as an oracle in order to filter these values and mark those that are invalid while only considering the valid expressions. So in this case, we filter out all of the values that are all invalid, and we will have only the halt formula, which is going to be written to the cell A6 as a concrete formula before continuing with the execution. Now that we have seen some examples and how the solver backend works, let's have a look at how this works in practice. So let's have a look at the malware sample analysis. This sample is a sample which was observed during the last 3 months and reported during the last 3 months. It is a fairly complex sample composed of multiple stages and 2D obfuscation routines. What you can see in red in the content flow graph are the errored or pruned branches due to our concretization strategy, while what you can see in green is the symbolic payload, which are all those cells that depends on environment variables and that we need to concretize when executing them in order to correctly execute the sample. This sample we start executing from the deobfuscation routine 1, which implements a simple transposition cipher which is used to deobfuscate only the first stage. This cipher will loop through all the payloads and through all the characters and generate from the obfuscated payload the deobfuscated payload for the stage 1. This looks something like this. The malware sample will simply rearrange some values from memory and thus generated the obfuscated payload. After deobfuscating the payload, it will start executing stage 1, which is a simple stage that only spawns a new process as an evasion technique in order to confuse static and dynamic analysis, and it will initialize the deobfuscation of the next stage. Then we will execute the deobfuscation routine 2, which is slightly different from what we have seen in the obfuscation routine 1, and in this case is an implementation of Vigna cipher, which is still fairly simple. This is used with different decryption keys in order to deobfuscate the second, third, and fourth stage of the malware execution. The Vigna cipher will start from the obfuscated version of the payload, shift it considering the decryption key, and finally generate the deobfuscated payload. So after the deobfuscation, we will execute stage 2, which will write 5 characters of the final decryption key, and these characters are generated using different evasion techniques. For example, the malware will check for alternate data streams, or ADTs. It will check some environment configuration, or the consistency of the system clock. What is interesting to note here is that the malware will not simply abort execution if these values are not what it is expecting to see, but it will instead deobfuscate incorrectly. And this is why symbolic execution is interesting. So the second time that we run the deobfuscation routine 2, you can see as in the decryption key there are some symbolic values, and thus the decrypted payload is going to be symbolic. And indeed, you can see in the control flow graph for the stage 3 that most of the formulas that we execute will have to be concretized. Stage 3 is thus a symbolic stage and will write the 6th and 7th characters of the final decryption key. In order to generate these characters, the malware will execute some more evasion techniques, like checking for the file system implementation or checking for the Excel macro security settings. We will then run again the deobfuscation routine 2 before starting to execute the final stage of the malware. This final stage is the infection stage. The malware at this stage will download a malicious Windows DLL and register it using the rundll.exe executable. It is interesting to note how, first, as you can see in the control graph, again, this payload is completely symbolic. We will need to concretize every formula before executing it. And as you can see from the branch, in this specific sample, if the first download fails, the sample is configured in order to access a second endpoint in order to download the malicious DLL. Now you might be wondering, okay then, but why do I need to deobfuscate this sample? And the answer is that with the deobfuscation, we are able to extract some indicators of compromise that would otherwise be impossible to extract. Some examples of indicators of compromise are files that are accessed during the execution, other strings or other executables that are used, or URLs that are accessed in order to download the payload or to download other files that are used by the malware. So we will now look at our evaluation and comparison with other similar tools and techniques for the deobfuscation of XL4 samples. First, in order to evaluate our tool, we collected and analyzed roughly 4,700 samples which were reported and observed in the last 6 months. We classified these samples in roughly 480 clusters of distinct behavior. Many of these samples still have a very low detection rate in VirusTotal, which we think is interesting, and many are still undetected. What you can see in this table is the number of samples that can be correctly deobfuscated using a concrete approach or a symbolic approach. You can see how using a concrete deobfuscator, we can only deobfuscate correctly a little more than 1,800 samples or 320 clusters. While using Symbexcel, we are able to deobfuscate correctly more than 3,000 samples and more than 400 clusters. However, now if you look at the symbolic samples alone, which are the focus of our research and of our tool, you can see how with the complete deobfuscator you are able to deobfuscate correctly only very few symbolic samples and symbolic clusters, while with Symbexcel you are able to deobfuscate correctly more than 170 symbolic samples and 91 symbolic clusters of distinct behaviors. So now, as a conclusion, XL4 macros are still an ongoing and evolving threat. They are very difficult to analyze and to detect accurately due to the set of evasion techniques which are used in the modern waves of this kind of malwares. We believe the symbolic execution provides a way to analyze these samples which would otherwise be impossible or very hard to deobfuscate using a concrete deobfuscator. This would allow to accurately deobfuscate the samples and therefore accurately classify the samples as benign or malicious. So thank you for your attention. This is it for this talk. If you have any questions or comments, we will be here and very happy to answer them.